Welcome to discussion 16. In today's discussion, we'll be doing some practice problems from sections 3.5, 3.6, and 3.7. In this discussion video, we will do the derivative of arctangent of x. We'll derive a formula for that derivative. Okay, so this is problem number 6b from worksheet 7. We want to derive a formula for this derivative of arctangent of x. So we have a formula for what this derivative is. I don't want to just say that answer. I want to show where that comes from. So I want you to pause the video for 5 minutes to try this. 4, 3, 2, 1, pause it and try this one for 5 minutes. All right, let's talk about it together. So I'm going to let y be equal to arctan of x. So remember that arctan of x, that's just another way to say tangent inverse of x. And to take this derivative, I don't know how to take the derivative of tangent inverse, but I do know how to take the derivative of tangent. So let's rewrite this in terms of tangent. That would be tangent of y equals x. So the input and the output get switched. And now we can differentiate implicitly. Okay, because in this equation, the output variable y is defined implicitly because it's not isolated. All right, so we are going to take ddx of both sides. So ddx of tangent of y and ddx of the x. And when the variables are different, like on the left-hand side, we have to do a chain rule. So first I take the derivative of the outside function, the tangent part, and that derivative is secant squared. So we'll get secant squared of y, and then we multiply by the derivative of the inside, which is dy dx. And the derivative of 1 is going to be 0. Oh, whoops, sorry. Caught this. This shouldn't have been a 1. This should have been an x. And the derivative of x should be 1. Okay. And now, if I isolate dy dx is 1 over secant squared y, and that simplifies to cosine squared y. But I don't want to leave my answer like this in terms of the variable y, because the original function was in terms of x. Okay, so my idea is going to be, let's use the equation that we have already, tangent of y equals x, to write what we have, that cosine of y term, only in terms of x. That way I can get my derivative purely in terms of x. Okay, so I'm going to do this by drawing a right triangle. So I'm going to make a right triangle. And because tangent of y is equal to x, so y is the angle, I'm going to call one of these angles y. And it doesn't matter which one I pick. So maybe I'll pick this one. And tangent, using SOHCAHTOA, tangent is the opposite side over the adjacent side. And I can write the x as a fraction. X as a fraction is x over 1. So the simplest way to make the opposite over adjacent be equal to x over 1 is to let the opposite side be x and the adjacent side be 1. And now if I call the missing side the hypotenuse c, we can use Pythagorean theorem. So if I use Pythagorean theorem on this, we will get, let's see, we'll get 1 squared plus x squared equals c squared. And if I square root both sides, we'll get square root of 1 plus x squared equals c. Okay, so that's what c is going to be. I don't need to worry about a plus or minus because this hypotenuse is the length, and that can't be negative. Okay, so we are ready to plug in and write down what cosine of y is. So dy dx is cosine of y squared. Okay, so we're going to have something squared, and cosine is the adjacent side over the hypotenuse. So the adjacent is 1. The hypotenuse is the square root of 1 plus x squared. And when I square that whole thing, the numerator squared is 1. The denominator squared will get rid of the root, and I'll get 1 plus x squared. Okay, so therefore, remember these 3 dots mean therefore. Therefore, the derivative of tangent inverse of x equals 1 over 1 plus x squared. 1 over 1 plus x squared. And I'm going to highlight that. We have just proven this formula.